let's now consider mapping between different coordinate frames. And we're going to stick to a two-dimensional world to keep things nice and simple. And what we're interested in is how do we represent the position of something in one frame, and then on the basis of that information, how do we then represent it in the other frame? So let's consider this object, which is located somewhere in space, but it's going to be fixed all the time, so it's not moving anywhere. And first of all, we want to know, where is the location of this object with respect to coordinate frame A? And the important things about coordinate frame A is it's got an origin, right? First of all, it's got an origin in it. Within that frame, the origin is always going to be 0, 0, right? So it's within that frame, that's its origin. And what it's got is directions for X and directions for Y. If it was three-dimensional, it'd have a Z as well. So we need to know then, within this, to represent with position within this frame, we have to find out how far along the X-axis from the origin this thing is, and how far along the Y-axis. And this particular case, it's actually quite easy. So it's just 8 and 1 respectively. Right? So that is the representation of this point in frame A. Now, we can have exactly the same object and exactly the same place in actual space, but then we're going to look at it from another frame, right? From the perspective of another frame, which is located, in this case, a little bit further away. And again, when we represent location within this frame, now what we care about is how far, in terms of its x-axis and its y-axis, is this object away from the origin of this frame. Now, first of all, we notice that the frames actually are lining up. So the x on both of them are going to be the same, and the y is going to be, both of them is going to be just the same. That's not always the case, but we're just keeping it simple here. And what we see now is within frame B, position is represented by 13, 4, right? So different values, but the position of the actual thing in real space is exactly the same. So what's the relationship between the two frames? Well, we can see that the origins are actually separated by 5, 3, basically 5 in the x-axis and 3 in the y. It's very easy to say which axis it's in terms of in this particular case, because we've obviously got them aligned anyway, right? So both of the axes align anyway. That makes life a lot easier to start with, but we'll worry about that in a second. So therefore, what we can see is, we have to calculate the distance between the origins. And if we want to now represent something that we have in frame A, in terms of frame B, what we've got to do is we've got to add on to what we have in frame A, we've got to add on this additional distance, right? So we've got to add on the translation 5, 3. And if we did that, we can map from one frame to the other frame, right? So what we're saying is, the point represented in frame B, that's one down here, is the translation between A and B, that's this distance here, right, between the origins, plus whatever the value is of the point represented in frame A, right? And in this case, it's just going to be, we've got the value for P, the value in frame B is going to be 5, it's a vector 5, 3, added on to the position within this frame A, which is 8, 1. And what we end up with is then the location of this object within frame B. But we can, like I said, we can actually get it by calculating this shift and adding it on to the value that we had for frame A, right? So we wouldn't necessarily want to do it all from first principles. We always want to do this. And this is a general problem. This is what we want to do. We're representing something in one frame, and we want to know what it is in the other frame. And I gave this example before. Here's an object. We represent it, within the frame of the camera, right? And it tells you where it thinks this object is, but it's using its axes. It's whichever direction they happen to be pointing. It's telling you how far it is along its x-axis, how far it is along its y and its z, with respect to its origin. And like I said, if we want this little robot, it can't reach obviously in this particular case, but if we want this little robot to actually move its endpoint to actually do something with this object, what we want is, we want to know where this object is in the frame of the robot, right? So, in that particular case, it's in the frame of the base, right? So, if you know the frame of the base and you know your forward kinematics, we can do the rest anyway. So that's what we want to do. Now, generally, like I said, we've got this issue that the frames don't line up, right? So in this particular case, some of the directions are flipped and some of the axes are interchanged, but in general, they could be completely at a different angle. So what we've got to do is we've got to have a way of mapping from one frame to another frame, given that this frame could be, that there could be a rotation between the frames and there could also be a shift between the frames. Right, so we need to deal with rotation as well as translation of coordinates. So in a case where the frames basically just have directions which basically are either exchanged or pointing in opposite directions, it sometimes can be quite easy to see what these would be. So in this particular case, we can see what we now call in x in frame A relates to negative x in frame B. So there's a relationship between frame A x-axis and frame B x-axis. It's basically the negative value of it. If we then look at YA, right, you can see that YA, the direction that we've got, is going into the page. It's a bit difficult to follow in this case. This now relates to the opposite direction to what frame B has got for Z. So YA equals minus ZB, right? And if we then look at ZA, what does that correspond to? Well, ZA is going up here. Another one is coming down, but they still aren't at arbitrary angles. They are exactly, if you like, in opposite directions. So in this case, ZA is minus YB. Now you could write that in matrix form. We want to know what things are in frame A in terms of what things were in frame B. And you can see we can implement this relation quite easily by, we've done the inspection, we've flipped things round, and we can say ZA equals minus XB. Yeah, so there's a minus there and a 0, 0 there. YA equals minus ZB. That's what we had here. And ZA equals minus YB. So in this particular case, we can just build up, if you like, the rotation matrix component by hand, just by inspecting what the actual frame directions are doing. And that's sometimes a nice thing to be able to do. It's certainly not, it's worth trying if you can, just to check things, if nothing else. But we've already discussed, right, in rotation, I'm just going to go back to the two-dimensional version of that. We've already said, we can already work out mapping from frame 1 to frame 0. And that's exactly what we've just done, right? We're mapping from one frame to another. And if there's a rotation involved, in this case it's a rotation around the origin, and we'll deal with the translation afterwards. We know that if this was, let's say, an XY plane that's rotating in, so in other words, if this was three-dimensional, the Z-axis would be coming out the page, wouldn't it? So we already know that to get from frame representation of a point in frame 1, we just multiply by the rotation matrix. Okay, so the rotation matrix in this case, this will map from frame 1 to frame 0, is simply the rotation matrix for the rotation around the origin in the XY plane, which is effectively going to be around the Z-axis if it was coming out. So that's very nice. So we don't actually have to think about it any more than that. We've already done the maths. We've already worked out how to map between these two alignments. So what we can say is we look at this slightly more complicated shift in frames here now. We've got frame B and we've got frame A, but now frame B is rotated by theta, right? And it's rotated in positive theta because Z is coming out of the page. So if you put your finger up, put your thumb up, which way do basically the fingers go round, and you'll see that they go up that way. So theta is positive if it goes anti-clockwise as it's drawn here. So we know to align the axes, we've got this rotation matrix. We just put it in here. So values in B are then rotated to get directions in A, right? Now we can't, well, we can basically, we could just stick in 90 degrees there and we get the transformation matrix already for 90. That's just an example. But what we also want to do is we want to account for the fact that there's also a translation. So what we need to do is we need to, first of all, points in frame B, we rotate them by this rotation matrix, rotation between B and A, and then we add on the translation, right? So if we do that, we can map without any trouble at all between different frames. In this case, we're rotating it round the z-axis, right? But if your transformation was around a different axis, you'd have to look at that and say, yes, it's, or it might be around the x or something like that. But you can see that this is a very simple way of then getting representation of points in one frame into another frame.